introduce yourself.
Good evening, good afternoon to one and all. We have amongst us the eminent speaker, our director, Professor Devashish De, and a professor of our department, Professor Sriyankar Acharya, sir. Now we will start the inaugural session once we have the other eminent dignitaries with us. Okay, we have Dr. Parthapratim Lahiri, the registrar of our university, with us. Good afternoon and welcome you, sir. We have Honorable Vice Chancellor, sir, amongst us. So, and also Professor Mustaq A. Siddiqui, Honorable Vice Chancellor of IUST, Islamic Jammu and Kashmir, amongst us. So, a warm welcome to one and all. Am I audible clearly?
Yes, yes. Yes.
Okay. A warm welcome to one and all. Myself, Dr. Suparna Bishwas, Associate Professor and Head of the Department, Computer Science and Engineering, and Dr. Sriparna Saha, Assistant Professor, Department of Computer Science and Engineering, take this opportunity on behalf of the organizing committee to welcome today's August gathering in this online faculty development program on intelligent computing. Myself, the program coordinator, and Dr. Sriparna Saha, the program co-coordinator, takes this privilege to welcome all. This 5-day long faculty development program from 11 September to 15 September is being organized by the Department of Computer Science and Engineering, Maulana Abul Kalam Azad University of Technology, West Bengal, in association with Islamic University of Science and Technology, Jammu and Kashmir, and this program is funded by Take It 3 of our university. This event is being organized with the pioneering direction and motivation from our Honorable Vice Chancellor, Sir, Professor Dr. Shoikat Moitro. He always immensely inspires us to organize such events where thoughtful ideas can be exchanged beyond the boundaries and collaboration could be possible. A warm welcome to you, sir. Please chair the session. Sir.
Thank you. You continue with the introduction of other speakers.
Yes, sir. We have Honorable Vice Chancellor Professor Mustaq A. Siddiqui, Islamic University of Science and Technology, Jammu and Kashmir, amongst us. A warm welcome and heartfelt thanks to you, sir, for your kind presence in this program. Welcome you, sir. Okay, so
he's not
Sir is joining, ma'am. Please continue, ma'am.
Okay. So next, we would like to welcome the registrar of our university, Dr. Parthapratim Lahiri. The support we get from him, not only during this particular organization of FDP, but all through our mundane activities is noteworthy in itself. Welcome you, sir, in this on inaugural session of this FDP program.
Thank you very much. Please continue.
Welcome. We welcome Professor Dr. Devashish De, Professor, Department of Computer Science and Engineering, and also the Director of the School of Computational Science in this inaugural session. Welcome you, sir.
Thank you.
Next, we welcome Professor Dr. Sriyankar Acharya, Professor of the Department of Computer Science and Engineering in this inaugural session. Welcome you, sir, in this program.
Thank you.
Thank you.
Thank you all. And also we have the speaker, today's speaker of the technical session that will be after this inaugural session is over. The speaker, eminent speaker is with us, Dr. Arup Kumar Sadhu. Also, we welcome you, sir. Okay. So now we will move on to, and without wasting any further time, we will hear our Honorable Vice Chancellor, sir. But before that, I must mention thanks to all our departmental faculty members who are organizing committee members of this event. Welcome you all. To briefly introduce about the 5-day-long faculty development program, main focus is on machine learning to artificial intelligence to pattern recognition to many emerging domains of intelligent computing. Each day, a distinguished speaker will deliberate his talk on his expertise field. The topics range from robotics to ethical issues to applications in several areas. On 5th day, all participants must submit feedback and quiz to get the participation certificate. Now we all are eagerly waiting to hear from our Honorable Vice Chancellor, sir. Sir, I am requesting you to please deliver a keynote speech and inaugurate this faculty development program. Sir. Maybe.
Can you hear us?
Yeah, can you hear me?
Yes,
Yes,
sir.
sir.
Yes.
I think we can start.
Sir, can you
Okay.
please?
So who will start? Should I start
Yes,
first?
sir. Yes, sir. Actually, okay, maybe the connection was lost. I'm just again
Okay.
welcome you that we are eagerly waiting to hear from our Honorable Vice Chancellor, sir. Sir, I'm requesting you to please deliver a keynote speech and inaugurate this faculty development program.
Okay, so far I can understand that this faculty development program is focusing on intelligent computing system. And intelligent computing system, as my idea goes, it makes use of computational methodologies that mimic nature-inspired processes to address real-world problems of high complexity, for which exact mathematical solution based on physical and statistical modeling are intractable. A common intelligent computational methodologies that include artificial intelligence, artificial neural network, then evolutionary computation, genetic algorithm, artificial immune systems, fuzzy logic, swarm intelligence, artificial life, virtual worlds, hybrid methodologies, and so on. And this intelligence computing is continuously changing a business scenario, and keeping up with this evolution technology world has become imperative for for different organizations, multinational organizations, to remain competitive. And this is very important in this sense, because in today's world, if we look all these multinational organizations, they are, this we can call it a razor-like competition for, this for grabbing the market. And based on this advancement of intelligent computing systems, this accelerating power and capabilities of modern computing that opened up a world of opportunities for businesses, and that are looking for streamline and optimizing operations. A computer, certainly it is not capable of thinking and act of their own, but there are very powerful systems that can simulate human behavior and job function. Cognitive computing, this is an emerging field, and it focuses on making computers more user-friendly. with an interface that understands moves for what the user wants, or more and more these identifications of these users' requirement. Cognitive computing, it encompasses technologies, includes like machine learning, natural language processing, artificial intelligence to form the foundation of intelligent systems that can supplement this productivity of human being. Now, one of the very important asset of each and every organization right now is data. Data is the new corporate currency. Every business generation that piles up numbers, statistics, and these are accumulating and getting generated on a regular basis. Finding meaningful patterns, that this data is the gateway to a gold mine of opportunity and profitability. Therefore, analytics, it can be used to describe, to improve and to predict business performance. So this relates to both internal factors, how this the conditions, this weather that may impact your business, and so on. So business that take advantage of this information available of them find themselves in a great position to make very informed decision and adapt very quickly to changing environments. So in this context, that all these concepts of all these, which is related to intelligent computing has tremendous potential of getting transformed into the business opportunity and possibility, and creating the possibility of generating a large numbers of these opportunities and potential for employments in future context. So with this, I believe that it will be very, very useful for all these learners, for all the participants to get meaningful insight from these faculty development programs. And as I said that in today's context, there is no dearth of this information. And if you have desire, you can always make yourself knowledgeable by getting the right kind of knowledge from digital platforms. There are n numbers of MOOCs courses available from at different platforms like Udacity, Coursera, edX, and different open course platforms. So if you have the desire and intention to understand more and more about these different these aspects of these of cognitive computing, or these different sorts of algorithms and different sorts of techniques which are very much essentials for intelligent computing systems, there are numbers of courses and numbers of the resources available. So with this faculty development program, try to get this right kind of perspective and right kind of test, and after that there is because this is a time for continuous upgradation and continuous relearning. So kindly engage yourselves in this exercise, this type of exercise, for getting yourselves more meaningful and more contextual in the future context. With this, I would like to congratulate Dr. Suparna Bishwas, Dr. Shiporna Saha, and all the faculty members of Computer Science and Engineering Department for organizing this faculty development program. This is very important topic, and my thanks goes to the resource persons who will be sharing their knowledges, will be delivering at these 5-day workshops, and I believe it will be immense help to all the participants over here. And I wish all of them a happy learning and useful learning. Thank you.
Thank you very much, sir, for your encouraging and illuminating words. With your kind direction and support, we are only being able to organize this 1-week FDP within such short period of time. Thank you very much, sir. Next, we would invite the Honorable Vice Chancellor, sir, from IUST Jammu and Kashmir, Islamic University of Science and Technology, to deliver his keynote speech.
Yeah, ma'am. Actually, I think he is not currently present with us.
Okay. Okay. Okay, then maybe he will be joining us, or there may be some link problem. And so next we move on to, and we would like to invite and welcome the registrar, Dr. Parthopratim Lahiri sir, to say a few words. Sir.
Thank you very much. Honorable Vice Chancellor, Professor Shaukat Moitra, Honorable Vice Chancellor of MAKAUT, Professor Devashish De, the Director, School of Computational Sciences, HOD, Dr. Suparna Bishas, other faculty members from the department, my other colleagues, and respected participants of this program. I am extremely thankful to you for inviting me for this inaugural session of this FDP program. And I would also like to congratulate you for arranging this kind of FDP through online mode during this pandemic situation. Now, I am not an expert on computer science, and also I do not know much about intelligent computing or computational intelligence. I was just searching Google, and I found that normally it's basically the subject where the computer performs specific tasks from data and experimental observation. So basically, intelligent computing or computational intelligence is a theory of design, application, and development of biologically and linguistically motivated computational programs. It plays a major role in developing successful intelligent systems, including games and cognitive development systems. So this I found from Google about intelligent computing. However, we can easily understand that nowadays this subject of computing, particularly intelligent computing, mobile computing, is extremely important for all of us, because whenever we are performing some tasks, nowadays we perform a lot of tasks using computers or our mobile phones, etc. And all the time there are a lot of computing activities so that we can perform those tasks successfully. So I hope that FDP will be a successful one. And once the participants go out to this FDP program, they'll be able to learn the subject and particularly get interest in the subject so that they can perform further research and development on this subject. I once again thank the Department of Computer Science and Engineering for organizing this FDP, and also thank them for giving me a chance to remain present in this inaugural program. Thank you very much. Thank you all.
Thank you so much, sir. As you have already told that today we are using artificial intelligence or pattern recognition technique in all of our daily life activities. Similarly, our 5-day FDP has different topics that are related to robotics, applications in electronic design. Not only that, ethics in AI, that will also be taught or it will be spoken in this particular FDP. Thank you so much, sir, to have you with us. We are overwhelmed to hear from you. This inspires us a lot. I take this opportunity to invite Dr. Devashish De, Professor, Department of Computer Science and Engineering, and also the Director of School of Computational Science, to deliver his welcome address. Sir, please.
Good afternoon. Elected Honorable Vice Chancellor, sir, and our Registrar sir for their constant support and encouragement to organize this FDP, along with IUS under World Bank program, TechHip 3. And this is the last month, and we are organizing lots of workshops. And this subject is correctly done committee and the experts from industry as well as from IIT and universities and IIT, NITs. So it is blend from both from academia and industry. Just I'm thinking that we are organizing so many workshops for last 5-6 months, but I don't know whether it's possible to develop certain website link to our department of university where we can we can keep our these lectures, as well as we can set up a virtual laboratory for artificial intelligence. I think that will be more sustainable, and the year everyone will get the help and the advice from experts, as well as we can develop the module wise. We have 15 faculties in computer science environment. At least we can design 10 to 12 experiments, and we can put it in the virtual lab like MHRD lab, and I think it is possible. And I think the experts from industry help us to brush up and to develop these models, so that everyone will get the benefit, starting from BTech students, and also we can give such reductions and recent trends. And by the process, I believe FDP will be successful. Another very important point that I just want to mention, that we are concentrating on the lecture materials, videos, and all things. So when I go for interview, then ask which book I followed. Current trend is only everywhere for YouTubes and online material. So I just want to you those who are this book is with me. AI book. It's a wonderful book for artificial intelligence. So if you're interested in AI, how it works, so you can go through this of AI, and it gives to Z idea how it works. So if you want to build up your background, you can go through this Russell book. I read almost every day chapter. So you can correlate. What AI, none of the research can happen. Actually, all the research and also the present day business analytics is AI based. So AI become the bread and butter for sustainable smart cities and society. So for this reason, I'll request someone should the initiative. I will be help with Sriparna Shuna. If we have our supervisor is here, who is expert in optimization process, we can build up virtual lab, and it will be sustainable, so that everyone, all the students of university as well as from IT and all the other universities will get the benefit. I hope we'll get a lot of knowledge of this next finance workshop. Thank you.
Thank you so much, sir. Just to mention, in my YouTube channel, there are the AI videos that has been based on this Russell and Norvig book. Just I'm promoting my YouTube channel. Okay, sir, thank you so much. Your cooperation and support is much served for such successful future events. Now, I would like to invite Professor Dr. Sriyankar Acharya to say a few words on this FDP. Sir, could you please?
Thank you, Sriparna. Honorable Vice Chancellor, sir, Registrar, and my colleagues. Already our Vice Chancellor, sir, Registrar, Dr. Devashish, the Director, they have already enlightened us about this FDP, which is based on intelligent computing. So I don't have much knowledge to add to their presentation. Only thing, I want to search the meaning of terms. Whenever some topic comes to me, I try to search the definition or meaning of the term. So our term is intelligent computing. The first question is, what is computing? If you see, if you think, if you search, you won't find any complete and unified definition what is computing. But still we go with this term. From our experience, we have made some definition. We say that computing is a process which is executed by a computer. Is it a definition? Or we may say that it's a process which uses computer operations. Is it a definition? Moreover, when we are talking about intelligent computing, the thing becomes more complicated. What is intelligent computing? Is computing itself is not intelligent? Is there any stupid computing? Why intelligent computing? What is the meaning of intelligence? There also no definition, no complete and unified definition of intelligence available in our science literature, but in philosophy there is a definition, but I am not going to that. So I am coming to the practical situation. This intelligent computing, from where it starts, why this topic is coming to us. Intelligent computing is some way to solve problems using computations, intelligent computations. And intelligence in practical way, it is defined as to acquire and apply our knowledge and skills. This cannot be a definition of intelligence, but it is accepted practically. So intelligent computing is to acquire knowledge and apply skills using computer for solving problem. Whenever I say the term problem, then once again, some new problem comes. So what is a problem? So I don't want to complicate this problem by defining a problem. In computer science, problems are dealt with their complexities, means they categorize problems into different classes. Some problems are called P-type. They are solvable in polynomial time using deterministic algorithms. Some problems are called NP-hard. So there is no deterministic algorithm available to solve them in polynomial time. Intelligent computing enters for solving hard problems. Wherever there is hard problems, we need intelligent computing. That starts with approximation algorithms, randomized algorithms, heuristic and meta-heuristic algorithms, evolutionary computation, nature-inspired algorithms, swarm intelligence, many things are there. One interesting point to notice is that these problems are hard and they are mostly optimization problems. To solve those problems, we don't have any analytical method. We don't have any deterministic algorithm to solve in polynomial time. Otherwise, it will take exponential time. You will die before solving your problem. So what the researchers observed that nature is the best optimizer. If you want to solve optimization problems or difficult problems, you have to learn from nature. You have to follow the natural processes. There are many natural processes which has inspired to develop our algorithms. So one process is annealing process, from molten state to crystallized state. When a metal goes from molten state to crystallized state, their annealing process is necessary, and that is simulated in an algorithm which is called simulated annealing. Our natural selection, which tells about survival of the fittest, that is followed, that principle is followed in genetic algorithms. We learn from insects, from animals. Animals' experience, we are utilizing animals' group experience, swarm experience. Means a colony of ants, how they minimize their path from nest to food source. That we have simulated and developed ant colony optimization. There are swarm of elephants, they are searching water. There is gray wolf optimization, they are actually hunting their prey. There are squirrels who travels from tree to tree for their food. All these phenomena. There are fireflies who moves in a group. There are flocks of birds. There are swarm of bees. All are our teacher to develop these type of intelligent computing algorithms. Though we claim ourselves intelligent, we are learning from animals and insects. That is to be noticed. So during this 5 days program, the participants, I hope they will learn, they will be enlightened through the illuminating lectures delivered by experts. And I hope for the best of this FDP program. I will thank who are organizing, and I'm also part of the department of CSE. So let us hope for the best. Thank you.
Thank you, sir. I hope our participants came to know about many of the techniques relevant, very much relevant, and maybe we will be hearing from our eminent speakers in coming 5 days. Thank you very much, sir, for your illuminating and informative words. So we are hearing all of our distinguished guests and speakers in inaugural session. All of our participants, including respected faculty members, research scholars, etc., are in proper direction for making this event even more meaningful, significant, knowledge building, and knowledge sharing process. I just want to mention that a WhatsApp group has been created for this FDP with the help of the webinar team for quick circulation of study materials, any announcements, any assignments related to this event to the participants for their reference. Once again, heartfelt thanks and gratitude to our Honorable Vice Chancellor, sir. In spite of his busy schedule and other important commitments, he is always with us to encourage and inspire us in all of such events. In past also, whenever our department has organized different webinars during this COVID crisis days, and also today, he is amongst us to inspire and encourage us. And we also express our heartfelt gratitude to all the distinguished guests in this inaugural session. From them, we have heard a lot of inspiring and illuminating words, and this can give a proper direction to proceed with the next technical session. So before we move on to, we would like to thank all our eminent guests, and if your time permits, then please remain with us. Sir, Vice Chancellor, sir, Honorable Vice Chancellor, sir. So we are at the end of this inaugural session, and with your kind
Thank you.
permission.
You continue your program. I have to leave because
Yes,
I
sir.
have to
Next
join
is
some
the
other
technical.
program.
Yes, an eminent speaker is
Okay.
already with us.
Okay,
So
okay. You start your
thank you
program.
very much, sir. Thank you very much, and thank you all. So now over to Dr. Sriparna Saha.
Thank you, everyone. Thank you, ma'am. Okay, so now we are going to start our technical session. In this 5-day long FDP, today we are going to learn about robotics. Today, our eminent speaker, Dr. Arup Kumar Sadhu from TCS Research and Innovation Lab is with us already. Welcome you, sir. I hope you can hear me. Thank you. So the speaker for today is Dr. Arup Kumar Sadhu. He has received his PhD in engineering degree in multi-robot coordination by reinforcement learning from Jadavpur University, Kolkata, India in 2017. He is currently with Research and Innovation of Tata Consultancy Services, Kolkata as a scientist. He has many publications in many international conferences and journals. His current research interests include artificial intelligence, reinforcement learning, robotics, path planning for robots, human-computer interaction, etc. Dr. Sadhu served as a reviewer for IEEE transactions on fuzzy systems and IEEE transactions on emerging topics in computational intelligence, neurocomputing, applied soft computing, IEEE transactions on neural network and learning systems, and International Journal of Software and Informatics. Today, he is going to enlighten us by giving his speech in planning and coordination for robots. Coordination and planning are closely related terminologies in the domain of multi-robot systems. Planning refers to the collection of feasible steps required to reach a predefined goal from a given position. However, coordination indicates skillful interaction among the robots to generate a feasible planning step. Therefore, coordination and planning mutually complements each other to address complex real-world problems. Coordination usually is of three different types: cooperation, competition, and mixed. As evident from their names, cooperation refers to improving the performance of the robots to serve complex goals, which otherwise seems to be very hard for an individual robot because of the restricted availability of hardware or software resources of the robots or deadline or energy limits of the task. Unlike cooperation, competition refers to serving conflicting goals by two teams of robots. For example, in robot soccer, the two teams compete to win the game. Here, each team plans both offensively and defensively to score goals and thus act competitively. Mixed coordination indicates a mixture of cooperation and competition. In the example of a soccer game, inter-team competition and intra-team cooperation is mixed coordination. Most of the common usage of coordination in robotics lies in cooperation of robots to serve a common goal. The talk deals with the cooperation of robots or robotic agents to efficiently complete a complex task. Thank you for this presentation, sir. So over to you, sir. Can you hear me? I think your microphone, you need to mute your microphone, sir.
Am I audible now?
Yeah.
Yeah,
Sir, please
thank you.
start the session.
Yeah. So thank you, Dr. Siparna. Now I'm sharing my screen. Is the screen visible?
Yes, sir.
Okay. So thank you for the invitation. Just a minute. So today the topic is planning and coordination for robots. So as the name evident and already described by Dr. Siparna in the brief, that planning and coordination are very much interlinked and mutually complements each other. So planning is the some feasible or meaningful steps to move a robot or robotic agent or any intelligent agent from one position to another, while coordination is the interaction or even skillful interaction among multiple robotic agents to solve a complex task. Basically, I will start here from the planning, that is single agent planning, then we will move towards the coordination, because coordination requires multiple intelligent agents, that is robot here. So let us move forward. So first we will go for planning using convex optimization. Now why convex optimization? Because convex optimization, from the theoretically, it will help us to move from local search towards the global optima. So this is the one of the most beneficial advantage from convex optimization. Now, without going much details of the theoretical and technical background, what we want to do here is that suppose there is a environment where there are cluttered or multiple obstacles are moving here and not moving, the static obstacles are there. So we need to, or we want to find out the where are the free spaces available. If we are able to identify the free spaces available, then we can easily tell the robot or direct the robotic agent to move from its current position towards the destination without avoiding any, without colliding with any obstacle. So how to do that? So basic idea is that there are two types of mainly region here considered. One is the convex region, another is the non-convex region. So what is convex region is basically, in language we can say, if there are multiple lines can be created by 2 points, then any line lies within this convex region, always lie within this region. No portion of the line will be out of this region. Then this type of regions are called convex region. Is my mouse pointer visible? Hello.
Yes, sir.
Okay, thank you. So it will be easy for me to. So now you can see that in case of non-convex region, if I draw a line, then some portion of the line are out of this region. So this is a problem because robot may hit obstacle. Maybe this region be an obstacle. So this is the basic idea. So we have to identify the entire free space as a collection of convex regions like this. Now, why we go for finding free space in a known environment? Because environment is already known. Then what is the point finding the free space? Because if we are able to find the free spaces, then what will happen? We don't have to check for obstacle while we are planning, which is the problem in case of other planners, because we have to identify or check the obstacle during the planning itself. Now, as evident, if the planner is not able to identify the obstacles during the planning, then obviously it will hit with the obstacle. Now, in case of without free space configuration based planning, the trajectory referred to the planning path will also may hit the obstacle and it will not lead to a global optima. Whereas in case of free space based configuration, what will happen? We can find the trajectory that is with path with specific velocity acceleration we can fix with the convex optimization, and it will also help us to reach the global optima. Now this is the one working principle. Here you can see that several convex regions are generated to identify the free spaces in presence of obstacle. Here this is an environment of 10 meter by 10 meter in 2D environment, and the black fields are the obstacles here, and the green circle, small circles are, let's say, some points. Here it is named as seed point, which will go and create such ellipses. And we all know that ellipse is the convex region. All ellipses are convex region. So the point is that the expansion of seed point creates convex region. So each seed expands and creates a convex region. And there are some hyperplanes you can see, which are just here line hyperplane means, which just separate the obstacles from the convex regions. And this paper is published in 2018 in Indoor Positioning and Navigation System, and one of part of this work. And next is another example of working principle, that is, here you can see that convex regions are overlapping each other and creating some connected regions. So this is another in 3D environment where the obstacle portions are not shown to for representation purpose, for better representation. So these are the some graphical output of the convex regions. Now only generating the convex regions are not enough, because convex region, if I draw a line with the convex region, then it may not hit obstacle, but when the line or path here of the convex region, it may hit on some obstacle or like that something. So we need some convex regions which are connected so that we can draw a continuous path from one point to another through these connected convex regions. Now here hyperplanes that I told here, the lines here, hyperplanes separates the obstacles and the convex regions. So what is happening here? The hyperplanes create a polytope inscribing the obstacles, inscribing the ellipsoid. And these contiguous convex regions are required for path planning. Now this after getting the connected convex regions, we'll create some undirected graph. So what will be the node for the undirected graph or vertex? Here the polytope node, polytope vertex, and the intersection between the polytopes are the node for the graph. So once we get the node graph for the planning, we can easily do any graph search algorithm and get the required path from start to goal. So this is the basic idea. Now we get a very much promising result in case of maze, because maze is a very difficult situation to find out path in case of randomized on sample based algorithm or all other state of the art algorithms. But in case of maze, we get a very much promising solution. And you can see that if we consider the comparison result, then performance index for the proposed, the last one, SFP, safe first planning, is the highest one, while others are very low compared to SFP. Even in case of PRM, that is probabilistic roadmap, if no path is found. In case of bidirectional rapidly exploring random tree and rapidly exploring random tree, the performance index is very low. So what is performance index? It is just the ratio of, here T, capital T is the time and capital L is the length of the path. So these are the just ratio of max of this one and this multiplication of this T and L average, where I is the ith algorithm. Now we did some experiment. This one is the crazy fly. This is a small mini drone. This with autopilot of PX4. You can see that there are some ball or circular shapes marker is fixed on top of the robot. So these are nothing but the marker. When we send some path, that is basically go from point A to point B, the robot will go from point A to B, but as currently we have not introduced any controller, so it may not follow the particular path. It will deviate from the path little bit. So to track that one, how much it is getting deviated, we use this marker to track its position, and we track its position using some localization method, that is camera, that is called OptiTrack system. The motion of the OptiTrack system is captured using OptiTrack. So these are some result in in experimental result. You can see the OptiTrack positions are marked by the red line, and algorithm, that is our proposed algorithm, is offered by the path is the green one. Now we'll share some video in the screen so that you can see what is happening, whatever the idea I am telling, based on that some simulation and experimental results. So this one is our work which is accepted by International Conference on Robotics and Automation, which is the top robotics conference in 2019. It was accepted. So the name is Safe First Path Planning in Cluttered Environment using Contiguous.
Sorry for interruption.
Yes,
sir, can you hear me?
Yes.
Can the audio level be increased more?
Audio level, yeah. Audio level in my system. Let me check. Is it okay now?
Yes, yes. It is. It is
Okay.
better. Yeah.
Okay.
Thank you. Thank you.
Thank you. Thank you. So now this is the video. So we have coded this one. So the video basically shows the determination of path by the proposed algorithm and implementation in 3D environment. And the experimental is conducted in a 350 cm by 270 cm by 70 cm workspace, and the proposed algorithm offers some designated waypoints where the robot needs to move, and it will move some intermediate, then finally reach to the goal position. So let's see. So we have coded this initially in MATLAB, and after that we have set the points to the robot in the robot. So you can see here the black vertical regions representing here obstacles. So we generate some random obstacles as we did in experiment. We took the from experimental platform the coordinates and put it in the simulation, so that we will get the exact path and fit it in the experimental platform. Now after this obstacle, you can see the green regions are representing the convex polytopes, and inside that there are some regions, blue regions. These are the ellipsoids. They are generating continuously. Once the seed is expanding, they are generating the polytopes. So they are all convex regions, and generating this region will be safe for planar, and they can move anywhere within these safe regions. So you can see here all the safe regions are marked here. Then none of the safe region intersect with the black region in the figure 2, that is free space generation written on top of it. And in the third one figure, you can see that there are some blue lines. These are just nothing but the edge of the graphs. So graph is generating using the polytope vertices as well as the intersection of the polytopes. So graph structure is created. Now once the graph structure is created, we'll get the path in the graph search. So my path is generated. Now we'll go for experimental platform. The generated waypoints are used by Crazyfly quadrotor to traverse from initial position to goal position, as you can see next. And its motion is captured by the OptiTrack system. So you can see in the left side the path what we get, and robots. There are two view in showing the robot. The small Crazyfly is flying, and as the Crazyfly will fly, you will get the path tracked by the OptiTrack in online. So it is trying to track the desired path, but little bit there is a deviation because there is no controller fitted. It's moving in open loop. Now it's moving to this towards its final goal. Now it will move down and reach its goal. So this is the path we obtained, and there is a little bit deviation from the actual calculated path, but it's always trying to track the trying to track the waypoints or designated points where it should move, and after that finally moving down. So this one was the one work. And next I want to share when this work is also suitable for when there will be millions of obstacles. In that situation also it can find a suitable path. So I have some simulation, and after that we will go for experiment where we can see there are number of obstacles are 10,000s. So these are the small obstacles you can see in the environment. So in this environment also it will be able to find path in an efficient way. So first we set the start position, and after that we'll set the goal position by clicking mouse. and it will continuously find the free space and find the path, and again find free space, again find the free space and path. In this way it will continuously get the path. You can see the path is generating in this figure. So it will continuously just finding. I'm moving a little bit forward because same thing is happening here. So it's about to reach the goal position. So total time required, I mean the computation time in because of the graphical user interface, it's taking little bit more to fetch the path and all these things. Computation time is very low, that is 2 seconds around. So within 2 seconds, it is computing the entire path from the start to goal in a 50 meter by 50 meter dimension environment. Now we'll see whether any portion of the path hit any obstacle or not. So it seems that there are some portion of the path is hitting the obstacle. So let us zoom this portion and check whether it is hitting or not. So one thing is here, when we plan, generally in case of simulation, we consider the robot is as point obstacle. But what is happening here, when we in real scenario, the robot is not a point obstacle, point robot. It is a some structure, some geometry, this type of thing. So we may plan in simulation like a point robot, but in real scenario, it will not work. So for that, what we did, we inflate the obstacle with respect to the robot dimension. That means we have just considering the bigger dimension of the obstacle as much the robot's dimension is. And after that we go for robot planning, so it will work very smoothly. So it's basically checking there is any heat or not, if there is any collision. Still now there is no collision. And also you can see it's keeping a very much big gap when there is a chance of keeping that gap. So it's keeping maximum possible gap between the obstacle positions. So it's just checking. Let's see whether any obstacle collision or not. The collision, let's see, zoom it. It's no, not a collision. So if there is just a touch with the obstacle, then it will not be a collision because we have inflated the obstacles. So it will not hit. So it's a long video to check all the path. So I'm just showing, I know that it will not hit, but for confirmation, I'm showing the everyone that it is not hitting. It seems there is a collision. Let's zoom it. No, just touched. So we're about to reach the goal point. Yeah, so successfully we have created a collision-free path in a 10,000 obstacle cluttered region. Now we'll see, in the previous cases we have seen that obstacle environment or map is already known or given. But if we want to simultaneously know the map as well as planning in parallel, then how to do that? So based on that, we have published a paper, the fifth one, this one, recently accepted. Let's video on that one. So this is a real-time autonomous navigation cluttered environment. So we have, in this experiment, we have already shown that if there is a cluttered narrow region, how it will manage to pass that region only in a small robot developed by in our lab TCS. So the concept here is that from the start, this is the resolution independent seed generation. This is another thing, the term I have mentioned, seed. So in case of seed generation, basically it happens, it depends on the environment map resolution. That is, what is the grid size, what is the voxel size in case of 3D. So in this case, the map resolution independent seed generation. So this is another topic. After that, what is happening that from the start position to goal position, it is not possible to go in a single jump. So for that, we need to have some sub goal positions in between start and goal. And after that sub goal generation, it will continuously check whether the sub goal is my goal position or not. If it is goal and reached, then and compare the sub goal, and again it will generate the seed and determine sub goal, and it will continue in this way. So this is the basic idea of this work. Now after that, now what is happening in case of experiment, we record some file that is called bag file. So what is bag file? It will, you can think that it is the collection of all pose, that is position, orientation information, all map information in a single file, that is called bag file. And that is generally used for robot operating system. In mostly it is called ROS. So rag file running through. So this is the ROS core. Before running ROS, we have to run the ROS core, and this is a bag file is running, which will provide the required pose information, that is position as well as orientation of the robot, and the from camera it will provide the map information, what is seen by the robot. So once I run the bag file, you can see the pose from the RGB snaps, simultaneous visualization and mapping. RGBD, D for depth, and RGB is the basic thing. And from the OptiTrack also we receive the pose. Why OptiTrack? Because this is used for ground truth, for comparison. So the pose are running. So these type pose are collected during the experiment. So now let's see how the robot is moving. So this is the arrow, this indicating the robot's pose, that is its current position and orientation. And the view you are seeing, it's basically seen by the robot. The robot is seeing that much, and based on that, this is the narrow region left. So within this narrow region, robot has to find a path from the start to goal. Now the robot will start moving from the start to goal. As it is recorded by robot, so I cannot show you the robot itself. It's a scene by robot that you are seeing. Now this is the map when robot is seeing in real raw camera view was like that, but what is processing or what is happening inside the robots, the calculation is like that. All the blacks are the obstacles and the whites are the free spaces. So as the robot is moving, you can see that the map is generating, it's updating its map and it's moving. So it start updating. So this is the basic idea for the free space based planning algorithm. Now only this one what I have discussed in details, but next I will cover lots of things but not in details, to have some overview what we are doing in our lab. Now as I discussed, there are lots of advantages regarding the free space based planning, but there are lots of disadvantages also, so we have to discuss that one also. So what is happening in free space based planning, it offers deterministic solution, but it is not suitable for high dimensional robotic plot configuration space. That is, high dimensional means suppose robotic agent, or in case of drone. So in case of drone, what is happening, we have to consider the its position as well as orientation, and their derivatives also. In total it becomes very difficult to handle such complex situations. So for that we prefer the RRT, that is sampling based motion planning, or PRM, that is probabilistic road mapping, and some learning based planning algorithms are preferred. So first let's go for sampling based planning algorithm. So one of the promising sampling based planning algorithm is the rapidly exploring random tree. So what is happening, what happened inside rapidly exploring random tree is that it has to first consider its C space. The C space basically the configuration space. It is the collection of robots or any robotic agents position as orientation. Position means you can say that XYZ position, and orientation is the roll pitch yaw. So this is the current C space, and it will generate the RRT, as its name indicates. It will generate some tree. So initially it will initialize its tree, and after that it will randomly generate some configuration space, and then connect it towards the nearest neighbor street. And in RRT, what is happening, the basically from its current position, robot generates some random control signal. So in case of drone, the control that the linear and rotation angular velocities. So linear velocities, you can think that x dot, y dot, z dot, and the angular angular velocities are, that is phi dot, psi dot, and phi theta psi dot, roll pitch yaw dot, that is orientation. Are generated, and to know the vehicle dynamics. So using the vehicle dynamics and the control signal, we'll estimate the future position or future configuration space of the robot. And then we go for checking the C1 and C2. What is C1 and C2? We have to, as I have mentioned earlier, that in case of free space planning, we don't have to check for obstacle during planning, but here we have to check the obstacle during the planning. So C1 is the checking for obstacle, and C2 is the checking for any kinodynamic constants, like whether the particular waypoint is achievable by the robot or not. All these things are checked, and if it is achievable, then it is okay. It will go for select the C space and go towards, move towards that point. But if it is not, then it will again generate some random configuration space, random control signal, and the same process is repeated. And it will continue until it finds the goals or final goal, until it will reach final goal or the maximum iteration reached. And then it will generate some trajectory. Trajectory means based on whatever the path it is obtained, with some that path with some particular velocity and all these things. One disadvantage of RRT is also that it don't have any closed loop control. So this is open research problem. And next we have used this RRT to have some finding path using differential drive robot. So what is differential drive robot is that you can think there is there are two wheels. You can send control signal common velocity in both wheels separately, and they can move in reverse direction or in same direction also. So what is happening in case of differential drive system, the configuration space you can assume is that the position of the robot as well as the orientation, that is x, y, theta is the configuration space of the robot. And here control signal, but just like you can see the car, driving of a car is just like a differential drive, you can think, assume. It's not like exactly same. So let like that its input is my steering as well as the velocity is my input, like input in my car, and the configuration space, its position, that is xy, and the orientation. So these are the parameters, that is one node of the tree, and these are the variation of xy, and these are the variation of the configuration space in orientation. And the list the down right one is the tree, and the top one is the path it's obtained. The same thing is done for drone also, quadcopter. We obtain some, in case of drone the xyz position is the input, in case and velocities are the input. So next go for the learning based planning. So what is happening in case of learning based planning, we mainly consider please tolerate little bit theoretical is thing is going to happen here. After that there are some nice videos. So what is happening in case of reinforcement learning? So you can think that while we human being, as a nice things talked about Professor Acharya, that we human claim ourselves intelligent, but mostly we learn from the nature basically. So what is happening in if we look at the human intelligence, we generally do some activities and get some reward or penalty, and based on that we update our memory and we reinforced ourselves and learn something like that. We also learn from creatures also. Similar thing can happen for machine also. It will, suppose there is an accident happen to the to some car, so it may note the particular steering input and all these velocities, so that it will not repeat it in future. So this is the basic idea of reinforcement learning. So it will act something and get some feedback from the environment and learn from the experience. So in case of single agent learning, so there are suppose there are 4 possible actions. So robot will do some activity. Suppose here R1 is my robot and it's creating some action, and it will move, it will create this is the goal position of the robot, this is the environment, if grid world environment, and this is the table of the queue table where all the queue values are getting updated. So what is happening, once robot takes some executes some action from state 1, let it will be for right action. So immediate reward for right action is 0 because it is not goal state. And using this queue learning update rule, it will update the queue value for state 1 for taking the right action using this update rule. So it becomes from 80.1 to 90. So this is the learning. In this way it will update all the queue values in the 0 filling cells. Now once the learning is completed, it will just take the queue values from particular state and get the maximum queue value and executes corresponding action. This is the basic idea. Now what is multi-agent coordination? Because in case of single agent thing, we or single robot thing, robot don't have to think about other thing what is happening inside, but in case of multiple robots involved, robot have to consider its own as well as the other robots actions and rewards also. So this situation becomes very complicated. So how to handle all these situations? So in this case it will happen that we have to do some a balanced situation among the robots, so that all the agents get united and get a common, reach a common decision and execute the task. Otherwise it will be a problem. So coordination is basically a skillful interaction as already discussed, and planning is a sequence of meaningful actions. So here we will consider, we will go for only cooperative coordination only. and there are some selected publications in this domain. So now, as discussed in single agent Q learning, if we want to transfer from single agent to multi-agent Q learning, then what will be the problem? Let's see this one. So what will happen in case of multi-agent? We have to consider other robot states also. So it becomes a joint state, like robot 1 is at state 1 and robot 2 is at state 2. So what will happen? The joint state become 1, 2. So from joint state 1, 2, robot executes action, then there will be multiple change in the system, because for robot 1, robot 2 will be dynamic, and for robot 2, robot 1 will be dynamic. So there will be problem. So there may not be a dynamic obstacle, but for them there are dynamic obstacles. So what we have to do, we have to get some joint optimal future reward determinant. That means we need to have some balanced situation among the robots, so that they will not deviate from their mutual goal or all these things. So these things can only be achieved using some equilibrium computation. So these are just state of the art work that are mass and correlated equilibrium. Now why we go for equilibrium? If we look at the left figure, this is a figure of truss and having at junction point A. This junction or this entire structure will be stable only if the summation of all these forces are equal to 0. So this is just like a, you can think the concept of equilibrium like that to understand concept of equilibrium. Or there is another, if a chair is drawn by two forces F1 and F2, then it will move towards the F only if both of the F1 and F2 will be applied. If any one, suppose F1 or F2 is removed, then it will not follow the path F in the direction of F. So this is just the concept of equilibrium. Now this is the Nash equilibrium concept. So here, suppose this one, this is LR, that is 2020, Mark 1 is my Nash equilibrium. So what will happen if any one of the robot R1 or R2 deviate from its Nash equilibrium? Suppose R1 deviates from its left action to right action, then it will see the equilibrium in this point. So what is happening? The system is losing because both the agents are not at their highest reward. Highest rewards are 2020, but now they are getting 10 minus 10. Similarly, also this can happen for R2 also. If R2 deviates, then both the agents will lose. That the system will lose. That is this one. So this is the point. From equilibrium, if any agent will deviate, then the entire system will lose. Now, how to compute this one? So this one, before looking at this one, let us have an example. This one. So there are two actions for robot 1, let A be, and robot 2 has two actions, that is XY. So if we go look at the top left cell, then you can simply obtain that AX will be the output. And if you look at the top right, then AY will be the output. And similarly, lower left will have AX output, and upper and lower right will be the BX output. So you can see that in the top row, we are varying the action of robot 2, but fixing the action of robot 1, that is A1, but varying the X and Y, that is varying the actions of robot 2. So what is the best response of robot 1 is that AX and AY. And for robot 2 also, we are varying in the second row, we are varying the actions of robot 1 while keeping the fixed actions of robot 2. So in this case, we are getting best responses of X and BY. So if we get the intersection of these two, that is AX, AY and AX, BY, and AX and BX, then we'll get the AX is the common solution. That is, AX is preferred by both the agents. So this is the Nash equilibrium. So in this way, Nash equilibrium is computed. The same thing is explained over here also in picture. Now we'll use this all the concept. I know that some of you are boring with this concept, but now allow me to show you some video. After using all these things, we'll have some nice simulations. We'll show the simulations one by one. First, we'll show a robot is just taking off, a drone is just taking off and moving somewhat forward and coming back to the same position. So you can see that the robot is moving up, the drone is moving up. So this work is developed by our colleague in our team. So it's moving and again coming back. So why I'm showing this one, because we can generally do or develop something step by step. So this one is the first simulation of robot. One robot is making ready. After that, we'll include much robot to make it more complex. Then now we'll introduce little bit more complex. Now we have 4 robots, 4 drones. They are taking off one by one, and they will now move forward and again come back. So these simulations are very nice, but there are lots of complex mathematical theories and all these things are behind. Now it will again go back in the same sequence to the start positions, maintaining the same height. So these are called Telo robots. Telo, its name is Telo. They cannot maintain the same position because the same position was the line, but they will land near about there. So the simulation platform is the Gazebo. In ROS, this is a open source platform. This is the Gazebo platform. This is mainly used for all robotic simulations. Now another simulation is, now they will form a rectangle like structure or square like structure rather. They form the square, take up and form square. They are maintaining the square. Now they are rotating while keeping the formation constant. After that, they will rotate for some time and land. Now we'll form a square using some classical control techniques. So here, and they will follow one leader agent. So there are 5 drones. So there are 5 drones, and first they will form a square, and one drone just above of them. It is, you can assume this is the leader one. So it will just move, and rest of the drones will follow it. So here we have used classical control. There is a paper published one of our colleague Mohit. So now they finally they will land. They landed. So just a minute. Let me switch off my video. Otherwise, I will run out of data.
Yes, sir. There is a button here.
It's now off.
Yeah, I've done.
You can,
Not
yeah,
off?
you can continue. Thank you. Yeah, it's off. Thank you.
Okay, thank you. So this square formation was published here by one of our colleague who is working with us now. Next is swarm triangle formulation. So this one is based on whatever the techniques I have described just before. We are using game theory and all the coordination and robot coordination and equilibrium techniques. So before going to the video, let me describe. So this is the just coding all this thing in Python. And in the right side, you can see there are some terminals in Ubuntu. So the top one is the Hector platform, where this type of gazebo window and all these drones are available. You can create so many environment like drones. And next one is the running code. And in the rightmost three from the bottom one, these three are the window where we can see the what are the control signal going to the robot or drone. And this window, that screen, it will show the reward and error plot while they are moving or towards maintaining the formation. So let's play the video. So the code is running, and you can see the reward is increasing continuously and error is decreasing continuously while the drones are moving towards each other. Initially they are in a straight line, but now they will move and form a triangle, equilateral triangle. And you can see the control signals are generating, not always, but as and when required. As the drones are moving closer each other in the trying to maintain the triangle, the error is decreasing, reward is increasing. You can see they are almost reached. Well, it can be seen almost they are about to triangle, but their distance is much. So the reward is not at reward is now zero 0.4 around. So it will increase more. It will reach up to highest reward is 1. When it will reach 1, yeah, it's reached 1, and error is about to 0. Yes, it's 0. And they have already reached the consensus, that is the triangle. They formed a triangle. Here I'm using the term consensus, which means a general agreement among the agents. So here general agreement is form the triangle. This is the agreement, so that all the agent will act accordingly. So you can see that it is almost a triangle from the top view I have shown. Now I'll do to test the as it is not a classical controller, it's a game theoretic controller. I will intentionally put some error in the system. That means I'll drag them to some different location, that is the break the consensus or triangle formulation. And as you see, once I break it, the error is introduced in the system and the reward is also decreased. Now they will again generate respective control signals, you can see here, and they will again form the triangle. You can see they are moving towards the triangle. And simultaneously rewards and errors are also decreasing. Reward is increasing and error is decreasing. You can see the robot is moving. It's almost reached. Now it's reached. This time we face some fluctuation because they are generating random control signal. That's why it may happen. We have to face some fluctuations like that, as it is random. Last time we have a smooth control, but this time it has some fluctuations. So it's reached the consensus again in spite of introducing additional error in the system manually. So we will see from the top whether it attend visually, whether it attends the triangle or not. It's attend. Yes. So next is the next topic is I will want to discuss what we did last year, that is Mohammed bin Zayed International Robotics Challenge. So this is a robotics challenge which was held at Abu Dhabi, organized by Khalifa University in there is a spelling mistake, in the year of 2020. So there are three challenges. Challenge one requires a team of robots or aerial robots, so three basically, mostly vehicles. So the team should locate and autonomously as well as track and snatch a ball. The ball is moving in the shape of 8 by some intruder drone. So that ball needs to be snatched by our drones and look and take it and snatch it and put it in a particular position. So this was the challenge one. Challenge two is like that we have to develop, so we have to create some structure or wall-like structure which is predefined or pre-described using some bricks and different size of bricks. So these bricks needs to be picked up by drones as well as the ground vehicles and create the pre-specified structure. The third challenge was the challenge 3, that is where a team of aerial vehicles and a ground vehicle need to collaborate and go for a firefighting in a high-rise building. In all the three challenges, we need a coordination as well as collaboration among the robots. Without this, it is impossible. So next we will go for some videos. Now, based on some challenge description, we have some video. This is openly accessible also. This video I have downloaded from openly. So this is 2019 edition challenge description. So this is a challenge one where you have UAV, unmanned aerial vehicle, have to capture this ball. This is a simulated video. The ball is rotating. Basically, the drone is rotating. So ball is hanged from the drone. So now this is our drone. It is flying. It's taking off, and it is identifying whether the ball, where is the ball. It's scanning using its sensor lidar. Once it will get, it will move towards that. Yes, now it snatched the ball. In simulation, it is showing. It seems to be so simple, but in real life, it is very difficult. I would like to say that only Institute of Beijing can do this automatically. Rest of none of in the world can do this. So now second challenge is the team of robots who need to construct a structure like this brick structure. So here you can see three type of bricks with different size and different colors. The brick size may different. They told that it may be of different color or 4 colors, maybe of different weights also. So now and they need to create this type of structure like that. Now they are going for the bricks to pick up the bricks using aerial as well as ground vehicles. They are simply picking and placing that. But when I will show you the real-time challenge videos, then you will understand how difficult these are. Because one thing is that when they are using the magnetic suction, the bricks are magnetic, so they are just attaching it and picking up. Now this is challenge 3, where a team of robots have to fight fires in a high-rise building like that. This is also very challenging because drone has to enter through the window. This is the most challenging thing in this challenge, entering through a window and coming out through a window, and also while staying inside the room, because there will be a lot of instability because of wall effect and ground effect because of the thrust generated by the drones or airflow, all these things. And this injecting water is also very much difficult because you may press mm, some water, put some water, it may not fall on a particular position where the fire is. This is also very difficult. Now the grand challenge, this is the simultaneously happening, all these three, nothing extra here. Now so what we trying to do, I'll show you all the reports here. First we'll show you the what we did in report 1. Basically here it is ISC is shown here because it was a collaboration between the Indian Institute of Science and Data Consultancy, Kolkata and Bangalore. So we worked collaboratively for this challenge. So this is the first report. This is the challenge 1 first. So these are the instruments. So DJI Matrix 100 is hello, GA drone, and all these things are used here. So this is just picture, and here you can see there are ultrasounds, GPS, and all these things are used. Cameras. This is a Mavic Pro and DJI Phantom 4, and these are the sensors, Logitech LiDAR, and NVIDIA Jetson TX2 is used, and DJI Manifold, all these things. These are the costly and high precision sensors, and these are very difficult to use them on the fly also, because mounting this thing is also very difficult, and operation of all these things is also difficult. Carrying is difficult because payload is also limited. Drones cannot carry all these things. These are lots of difficulties are there. So our in case of challenge 1, the approach was autonomous takeoff and then detection of drop zone, where the drop zone is where the ball need to be kept, and the landing zone where it will go and land finally, because landing in a particular position is also very difficult position for drone nowadays till today. And detection of target drone is one of the important point here, and after that detection of ball, and then ball tracking using visual surveying, and grab the ball and autonomously landing. Now we'll first show the autonomous takeoff and landing, because in the first report we complete all the things step by step, because it's an entire challenge. So generate piecewise all the solutions, make the ready, and later we compile everything. So you can see that this video is done by drone only, so that's why you can see the shadow of the drone. And this place is basically the airfield of India ISC Bangalore. We did experiments there, and we also used to go there from Kolkata to do experiments there. And this is the ball is getting tracked, as well as drone is detecting by the other drone. This video is done by the drone only because you can see the propeller coming sometimes. This one. Now this is the ball tracking again when the drone is moving in the shape of 8. Another drone is moving shape of 8. The ball is tracking. Here you can see the depth map. It's very difficult to grab the ball. So just last video we just tried to track the ball and everything, and next one we are going to show so that when the ball is static we just want to grab it because everything is doing in a single step parallel. So now I'm going to grab ball autonomously. So there is a net like structure and it's trying to grab, so it's grabbed it. And now challenge 2, whatever we've done in our first report, that is in April 2019 I think. So here we have to construct a structure using some bricks. So here also the hardware used are DJI matrix because we need a heavy drone like that to pick the bricks using magnetic gripper. And also if we take too much powerful drone, then there will be also problem because of the downwards the brick will fly. I will show you some of the videos. And this one is our in-house build ground vehicle in TCS. And next is the UR5 manipulator. These are Velodyne LiDAR, one of the most precious and state-of-the-art LiDAR. And NVIDIA Jetson, all these things are used. And this approach is that here we have to identify first where is the brick pile is. Once we identify the brick piles, then we have to pick up the bricks and place the bricks using aerial and unmanned aerial vehicles and unmanned ground vehicles. And cooperative brick picking is also we are trying to use in this one, but that one is simulated right now in this report. And next we will go for aerial vehicle navigation between big files and building sites. That is robot need to autonomously move from the brick pile position towards the site where the structure needs to be created.
Hello, sir. Just
Yes.
a second.
Yes.
Actually, Honorable Vice Chancellor, sir, of IUST has joined, Professor Mustaki
Okay.
Siddiqui. Can we just take 10 minutes break so that we can welcome him?
Yeah.
It will be
Sure.
helpful for us.
Sure.
Okay.
Sure.
Thank you, sir. So, yes, over to you, Suparna ma'am. Can you please welcome him?
Yeah, thank you, Sriparna ma'am. Very good afternoon, sir, and a warm welcome to our faculty development program on intelligent computing. Sir, and in the beginning, there may be some network issues and all that, so that we couldn't hear you. So I would like to invite you to say a few enlightening words to the August gathering of today's FDP program.
Okay, thank you, Professor Biswas. I'm sorry, I was also late. I was in a meeting, so I'm out of station, also from Kashmir, so I'm out of Kashmir. It gives me great pleasure to see the MAKAUT and the IUST working together to bring to the stakeholders, students, faculty, everybody on board. What is the new norm? New norm is, of course, we have to actually, work on everything on the webinars and the video conferencing for the time being, as long as the COVID is going to stay with us. And I'm also happy that I was actually listening to the technical lecture by the faculty from the Indian Institute of Science, Bangalore, and it's really, amusing to me that that our students are getting a lot of feedback, a lot of technical lectures from very specialists in the field, and I'm sure it will bring out out of our student community the best, which is going to be for more time on this globe, because we know that I mean the new norm is going to stay for some more time. So therefore, I would not come in between the technical lecture which is being delivered. I wish you all best, and I'm also, you know, still in the meeting. I would love to listen a couple of lectures more. So I'm there. I'm not going to leave the meeting now because I have 1.5 hours free for this. I will be listening to some of the technical lectures. Thank you very much. Thanks for inviting me over these small words that I delivered. Thank you very much.
Thank you, Professor, for your kind words. We can understand that in spite of your busy schedule and other important commitments, within very short notice, rather I can say very short intimation or invitation, you are amongst us. Again, thank you very much. We are inspired by your words, sir. So please remain with us, and we are also very thankful to you that you will be remaining with us for maybe few lectures as your schedule permits. Thank you very much, sir. And also we are enjoying the collaborative work that we are doing with support of TechIP with IUST. Thank you very much, sir.
Welcome.
So now we will continue with the technical session. Over to our eminent speaker.
Yeah, thank you.
Thank you.
Thank you, madam. Is it a screen? Visible?
Yes, sir.
So we are with the challenge 2. The technique for the challenge 2 is to identify the brick file first, and then robot need to move from the brick file position towards the position where the structure will be, and need a coordination among the aerial as well as on base. And after that, it always need the autonomous movement from the big distance towards the building site or where the structure need to be built. It's not playing. It's playing. So next we'll show. So first is brick detection. So first brick detection, we need to generate. We have initially generated some point cloud. So basically, point cloud is, you can think just some point, basically collection of points. If there is anything, obstacle or something, any object, so it will return some point from that particular point. This is basically point cloud. If there is nothing, then it will not return the XYZ position. So if there is something, it will return some point, and collection of all these points is called point cloud, you can say. So this is a monocular camera. This detecting brick is getting detected. Now brick pick and place. So initially this is in simulation in our challenge 1, in our report 1. So the real, this is also done in Gazebo. This is the most state-of-the-art simulator for robotic simulation. And after that, we have tested in our in-house developed robot. This is a Mo Picker. This robot is Mo Picker. We named it Mo Picker. Now it's taking the brick on its back. And this is the construction site. It is shown here. So it need to move autonomously from that brick piles position toward this construction site. So now it will move. And it will place the box, magnetic box, the box of Amazon delivery, like that. Now this is using aerial vehicle, so it is also pricking the bricks using simulator, using magnetic simulator. So this is when drone is just down, it is reducing its propeller speeds, because if it will keep the propeller speed high, then the bricks will move away from here and there because of this airflow. Now cooperation between the aerial vehicles to shift a big structure like big for one aerial vehicle. The autonomous navigation between big files. So this is the big files. This one, you can see the drone's shadow taking the image, taking the, this is a construction site identified. Now there are so many bricks. I have identified some brick. It will go the construction site identification. So this is just like autonomous navigation testing, whether it is moving from the brick pile location towards the construction location. Now this is a challenge 3 of robots fight for fire in a high-rise building. So we have used some 960 and some in-house designated that is same one previous to in robot. These are also metric and metric 100, and this is also in-house build ground vehicle developed in small. This is a small vehicle. Test our algorithm first, because handling the such board is very difficult. So we generally algorithm in small vehicle and Intel RealSense and other cameras. So here approach is that we have here the main point is that you needs to explore the arena and detect the building structure. Where is the entry point of the building? Where are the windows? Because in high-rise building, you have identified building with its entry point, that is like door, window, all these things. And next we have to also identify the fire locations exactly, so that we can put some water or some cover some clothes or all these things on the fire. Douse, and you have the coordinates. Next we have to detect, and yeah, so these are the main points. So now we'll go for the experiment. Now mapping and exploration, for that we did some first in simulation environment, that is also in gazebo. So here there is a high-rise building. So 3 aerial vehicles are moving, that is you can say better orbiting the building structure, so that can identify where is the fire location and all these things, and window if there is any casualty like that. Uh, Another thing is in this challenge is that autonomous navigation through a window. There is a drone window. What will happen? Suddenly it will get some ground. It is on top of the window. So there will be huge ground effect. Because of that, drone becomes variable, and when it enters inside building, it becomes a room instead of a area. It becomes a room. So all the way from as well as ground effect, it have to tolerate the wall effect also. So behavior of drone very unstable in such situations. So these are very difficult things. And also identification of the window is also challenging. So here we did using visual surveying, and the drone is passing through the window. So this is the orb slam based guidance. So here you can see the point clouds and the window is getting identified. the fire detection. I'll show some details video on this fire detection. So this one just in introduction, just basic. This is a small. We are testing it in last year. So here, once it's detecting fire, you can add here. And these are another experimental setup, how to move in a complex structure. And so these are our teams from ISC and TCS. So this is first. Now in second report, I want to see, I want to show some more interesting thing. So this is a challenge again. Improvement here I want to show. I'm tracking the common thing. So the same type of hardwares are used, and this one is the new hardware. You can see the PICSOC. This one, the PICSOC, the autopilot. The process and in new thing what we did in the communication coordinated in search. The thing in challenge is that in challenge one there will be some balloon in the environment. So if anyone the drone can pop the balloons, then there will be marking, positive marking for that. And the second challenge did also. I'll show the in the second video. This one, the multi-UGV coordinate. So is coordinating among. So this one environment to identify the moving drone easily. So which zone it is, so that you can easily grab the ball. Exactly. This is the is what is observed. Other is the pursuer drones, what it is observing. Both two are shown. So it is observing the drone is moving. Another one is observing that some drone to grab it. I think some problem with the video. There is some problem. Some report. Now drone takes off. I think there is some problem with this video. So the same thing in second report also. So, but I don't know what happened with the video. So I'm going to the next video. This is the challenge. Actual challenge happened in Abu Dhabi. We have some videos. This is for challenge one. So the challenge one, this is the structure in Abu Dhabi. So these are the drones. Challenge one, we have to snatch the ball and pop some balloons. And these are in all So no, it's not started yet. Now balloons are popping. You can see this one is balloon and it's popping. The drone is popping the balloons. One balloons popped in autonomously. Another balloons is going to pop up. And this is the drone, I think. Yeah, it came. This is the shape moving drone. You can see the drone started moving with the ball, and this is our drone trying to grab the ball. It's moving here. This one is the actually the distance is very, so then map environment is area and not when it's coming close you can get bigger view. It's moving very fast. It's trying to grab but cannot. Cannot hold the ball, disengage, cannot hold it and drop it, disengage the ball, release the ball from the intruder drone. Now it will taking the landing. So that much we can do in challenge 1. The challenge 1 is already only completed autonomously by Beijing Institute of Technology, and none of the in the world complete this. Complete successfully. Next, some video of challenge 2, what happened in Abu Dhabi. So this is the competition ground, and here you can see there are lots of bricks are kept over here, and this is the structure. In this structure we have to put the bricks on top of it. It is very difficult because once you put the brick, it will move here and there because of the downwards coming from the drones. And in the another side there is a aerial vehicle, ground vehicle. It will take bricks from these piles and you take it and go to the construction site. First is it has to adjust its position and orientation, because in the controlled environment inside our lab we did this very smoothly, but when the actual scenario came it's very difficult because the bricks are very not that much light, also small, also not small, it's very weak bricks. Now the is adjusting itself to have, so it's actually 30 minutes video, so I'm dragging little bit. So it's trying to get now in this side you can have aerial vehicles where they are picking the bricks and they are trying to put it on top of it, but you can see that they are trying their best. But let's see what happened. It cannot place. Yeah, it's fall here. Again, it cannot place. So this also it cannot grab any brick till now. It's trying to adjust itself. I'm dragging a little bit. It's a big video. Again, drones are trying to pick some bricks. It has picked a very bigger one. But let's see whether it can manage or not. Oh, it's done. The bigger brick is placed here. Now again. Another brick is placed. So the more brick the drone can place, the team will get. This is the and now it is able to grab some bricks, the ground vehicle also. Now pick another bricks. The more bricks, more points. And if the someone can do in autonomous mode, then there will be more marking. The manual mode is also allowed it, but there will be less point in that case. Yep, the ground vehicle managed to pick some bricks. Now it's carrying and adjusting itself to move to the construction site. Again, another big bricks placed. This one. One brick falls here. Another falls here trying. The drones are trying to put more bricks. There are lots of bricks left here. Another drone is here. It's reserved. These are. consequence, more the we are able to place some of the bricks autonomously and some manually also. And this one is the experiment done. Now we have to collect all the bricks, and volunteers entered there and fixing drones by our team. Abu Dhabi. Moving back to the home position and landing here. It's landed. So this one is the challenge 2 video, and now we go for challenge 3 video, whatever we did in Abu Dhabi. So in case of challenge 3, you can see this one is the drone which we have developed in our TCS. It's a rocker boogie mechanism. This is just like a Mars rover, which is developed by us. And this is the top one. You can see there is a LiDAR, there is GPS and 6 wheel. What is the point here, that it can move in any surface, the rough terrain also. So this is the most advantage of this drone. In Mars, generally this type of vehicles are sent. And this is the drone. It's starts flying to identify the fire and all these things. Actually, there are two types of two types of fires, and one is the hot objects. Identification of hot object is done by thermal sensors, thermal camera, and identification of real fire is also done by thermal camera, and some simulated fire like silk like structure. This one you can see here, this one is the simulated fire. It's not actually fire. Some air is coming from top and from bottom, from air, and light is coming from bottom, and some silk structure is flying on that, and it looks like a fire. So this one is just identified using some camera and all these things. So the drone is moving to identify fire, looking at the building and trying to orbit him. And on that side, ground vehicle is moving towards the building. It's identified the door, and it is moving inside the door, moving towards that. And there is a water bottle fixed behind it, and there is a sprayer mechanism using pump on front of it, so that it can spray water as and when required, or fire identified once fire identified. And in that side, the drones have identified, trying to identify fires. But as I told you, that very difficult. Once they move towards a wall, it will face a very high wall effect. So due to that, it will face a lot of disturbances. And when it will try to enter through window, it will also face the same issue. I think it cannot. Fire in the facade. Another drone trying to take up. Actually, there are battery issue also. This one already flying here, the top one. The drone is flying here. Here you can see this one. Moving towards the building structure. Actually, this drone is cannot trying to fly, but what is happening? It cannot. The problem was that it was not able to identify GPS, because there was a problem that once until it gets some GPS location, it cannot take off. So this is a problem happening. And as because there are lots of metal structures are there, so we faced a lot, not only us, all the teams are facing, we're facing the access of GPS. There are lots of issue on GPS accessing. So this was the main problem sometimes we are facing. And you can see the drone is trying to enter through the window. It's entered. Now, once it entered, it faced a lot of difficulty. It becomes unstable and cannot manage after that. And we cannot show what inside what is happening in the area ground vehicle, because ground vehicle managed to identify some fires and it poured some water on that to douse the fire. And this is a simulated fire. You can see this one is flying. This one is trying to put some water, but cannot. Once it go towards the wall, it will face, it becomes unstable. It cannot. All the teams are facing same issue. No one can solve these things. So this one, these are the all about challenge 3. What is now next? We have some specific moments video like window detection, building detection, fire detection, and all these things. So let's show some.
Hello, sir.
Yes, yes.
With your due permission, do you want to have a 5 minutes break? If you want, we can have it now,
Uh,
or otherwise you can continue.
if you can, otherwise I can continue.
Okay. So with taking the permission from all the eminent panelists over here, um, we are having a small break of 5 minutes. As
Okay.
due to this pandemic situation, we cannot offer you snacks. So you, all of you, the participants, please go have some bite or have some water on yourself, and we'll be starting this session only after the 5 minutes of the break. Thank you, everyone.
Okay.
Just
Okay.
a 5 minutes break will be coming within 5 minutes. Thank
Okay.
you, everyone. So welcome back everyone. We are back from the break and we are going to continue with the session with Dr. Sadhu. Sir, can you hear me?
Yes, yes, Dr. Suparna.
Yes. Please continue, sir.
Okay. So I'm now sharing my screen again.
Yes, sir.
Is it visible?
Yes, sir.
My presentation. Okay.
Yes, sir. Yes, sir.
Okay.
Presentation is
Okay.
visible.
Okay. Okay. Thank you. So we just left behind when now we want to share some specific moments like window detection and building detection, all other things. So for window detection, we'll show some video. So in the left side, you can see that there is a building like structure with a window shaped empty space. And in the right side, we can see the point cloud generation from the camera, which is seen by the camera carried by the drone. So there will be two reference frame you can see here. One is camera reference frame, another is the wall reference frame. Wall reference frame is fixed and camera is moving with the camera. So you can see the camera reference frame is moving, and the circle is the centroid of the window it is detecting. So it is detecting the window and it is about to move there. So it's entered inside the window. So this is what is happening inside the camera, and you can see here one of our colleague is sitting here. This is very risky. He is making some video when the drone is entering. So once entered the drone, we just immediately took it back manually, otherwise it may be dangerous. Now this is the another view of the same experiment. This one, left one is from the outside, taking camera from ground, and right one is the video from inside, how it looks. You can see there is a pipe boom is connected on the drone. It will spray some water. It's spraying water already started, and these are the simulated fire. You can see here the simulated fire. These are the target in this case. So this experiment was also conducted in airfield in ISC Bangalore by TCS. Now building detection demo. This one is this experiment is conducted in EcoSpace, Kolkata, in the Gitanjali Park. So this is the building detection. It detects building. This is the building. So our aim is to detect the building and orbit it by another drone. Building detection by another detects the building using LiDAR sensor, and it process all the computations are done on board in using some Jetson TX2 computation board. On board means everything is happening in the drone. So there is no offline or something server is there. Nothing is there. Computing in the drone itself. All the sensor data collection, everything is done there. Now once drone detects the building, and it will move towards the building to confirm, because it may detect another structures. So for confirmation, once we get some building like structure, we move towards it, closer to it, and confirm whether it is a building or not. Once we detect a building, we send the location of the building to another drone. That will happen after some time. Confirmed, and building is communicated to other drone, and that drone you can see here, it's taking off and it will moving towards the drone, towards the building, and it will start orbiting the drone to identify whether if there is any fires or like that, or where is the windows or possible entrance of the building. All these things are scanned by the drone. So these things we initially done in gazebo. Now this is the real experiment. So the video is not clear because it was dark at that time. It was about to sunset. So here we use the LiDAR based laser based sensor, and this is the what you shown last previously is the actual scenario, but what is happening inside you can see here. This white color is your building detected, seen by the LiDAR sensor, and the green is the drone which is orbiting the building, and red is the building drone which is just sending the information after detecting the drone. So this one specific moment. Next is the regarding I have some video for fire detection. So fire detection first we did in simulation. Here you can see that some a video. So in this video you can see here that there is no fire is written here. So once you will get some fire, it will send the information that there is fire. So actually this is happening with the rover. The rover just have shown the 6 wheels rover mechanism. So the camera is mounted on that and it is sending the signal, and the same video is also done using the rover also. The camera mounted on rover. That is real sense. Still now there is no fire. Here fire means the simulated fire, not the actual fire. So there is a fire, but it is too far, so it is not identifying this one. Now once it will get fire nearby, it will say that fire. I think there is a fire in the left. Yeah, it's a fire. Once it detects a fire, it will send there is a fire detection score with a high value near to 1. Now again on the fire, it will put some water on the fire and it will move towards another fire. Another fire is detected and it will again move towards there. So putting water on particular location of fire is also very difficult. So here you can see that we cannot put water in specific location at that time. Later we have corrected this one. Now it's coming back. So this is the video, what is happening, what the drone robot is viewing. Now we have another experiment. So this one. In the same video, I think this one. This is the same video. This is recorded by other camera, so I'm skipping this video. This one is the rover video. The ground vehicle is moving in search of fire and another drone is flying on top of it. You can see the shadow. So the video is recorded by the drone only. There is a down facing camera. Now it is identifying the fire and spraying some water. The first time it's identified fire, it sprayed water. Now again it will go and search for water. In this case, we have done all the processing inside this laptop. Now here you can see that in the black screen, once the fire will appear, it will be seen visible here. And this one we have done using deep learning, this fire identification. We train all possible fires using deep learning and then try to match if there is any fire-like thing. So after putting some water, it's again going back. Again, it's sensing some fire, so coming forward. Now, this one is another experiment. While planning and doing coordination, all the things, only planning is not enough for a uh, successful system. We need to estimate the position. In every time I have mentioned that robot need to have some pose information, that is the position as well as orientation information of the robot itself in its own frame as well as in the global frame. So for that we need to estimate the robot's position. Mm. So for that I'm showing this dynamic obstacle later. Let me show this one for state estimation. So this one is the state estimation. So this one is published in ICRA, done by one of our colleague. So here they have used the uh, actually what is happening to identify the state of a system. Generally, lots of state-of-the-art sensors are available, but is it possible without using sensor, using the model of the vehicle or all these things? So this is based on that information. So this video is vehicle moving randomly in a specific area. So it is using the dynamic model of the environment. So we put some weight on the robot and change the model of the environment, because its weight is changing, its model is automatically getting changed. And in spite of that, we are able to uh, estimate the vehicle's position in online. That is the estimate the position and orientation. So this is done in Kolkata EcoSpace office, in our office. This robot is also developed by us in-house. So here we have used the OptiTrack for ground truth. Here there is a marker, there is a white section is there. The marker is there kept one, so that it can be tracked using OptiTrack. So here is the weight is kept, so that the it can so that its model can be changed. So and we can have different model and test whether it is able to we are able to estimate the system's status or not. Now previous one you have seen that without weight. Now you are seeing with weight. You can see that it is following the same structure. You can see here in actual and model, and is a extended Kalman filter based. These are the plot of position. That is position. That is as I told, the estimation, basically estimation of position x and y. So position x, position y, and this is the Euclidean distance error. So its error is very low, in very low error. It's within 1 meter approximately. And one patent also accepted based on this work recently. Now I'm coming back to the dynamic obstacle detection. So this is basically based on some vision work. What is happening here is that in case of cooperative situation or coordination work, generally it happens existence of dynamic obstacles. So what happened, even in case of one agent, it will consider other moving agents as a dynamic agent. So we have to consider these things also. So one of our colleague doing work on that vision. Here you can see this is a gazebo environment, and this is his rooftop. So her daughter is just moving as a dynamic obstacle. His daughter is moving. Once it will move, she will move. You can see that the camera will track the dynamic obstacles and all other obstacles in the environment, including the static and dynamic both. So this is a very difficult work. It seems easy in simulation, but there are a lot of complex computations are there behind. So you can see once we move from this way, it's track this position. Now it is out of scene. She is out of scene. There is no obstacle, no moving obstacle. But it is updating the map as the camera. Now again she came. It's again updating, but it is static now. So now this is the map. So still it is noisy. It needs lot of processing, which is again another big challenge. So now we'll show some work on exploration, because while planning, only moving in an unknown environment, when the environment is known, then it is okay, or how much I can view in my camera view, that is also okay. But if I want to move, once we get once before if I want to move before moving in the entire environment, then I need to know the entire world map. So let's have some example on that. So let we have an actual world like this, and we want to explore the entire environment using some drone or something else. So how to do that? So we'll show some video on that. So this is also constructed environment in gazebo, and this is a drone. So this drone vehicle will explore the entire environment autonomously, and this will be the final output. Okay, so this is the constructed map. Now how this will come, I'll show you. So this is basically Octomap, one of the state-of-the-art work used to Octomap. These are box. So these are the created using Octomap. The map building is done using Octomap. So now how to build the map in 3D. So this is the work on that. Again, we did some computation in this work. So here drone started moving in the environment, and in the right side you can see building map, scanning its surroundings and building map in the arena. Whatever we have seen finally, that one it is building. So video is very big, it will take some time. So it is still exploring the entire environment. Actually, I cannot explain the entire theory what is happening because these are the TCS policy. So I cannot say what is happening behind this, but I can show the end result or demonstration like thing. So I'm dragging a little bit. It will take some time to explore the entire environment. So the maximum time generally it will take in this complex region, in this region. I'm dragging it. It's a very big video. Now I'm inviting speakers also for possible questions if you have. I think this is the last video.
Okay, so we are coming to the end. If the participants or the eminent panelists have any questions, please ask, or you can write it in the QA section. As we have only one question with us that we can take after this presentation. Please post your questions in the question answer section. If you have any doubt or you want to know anything much deeper.
Participants are requested to kindly post their questions Participants are requested to kindly post the question or any information to be known related to the topic in the question answer section or in the chat box. Ma'am, we can see that there are 3 questions in the question answer box.
Okay. Actually, I can see only 2 questions.
2 questions. First question is from anonymous
Uh,
attendee. How can the robots
okay,
drone?
I am just reading out the 2 questions. Then
Yes,
anything
ma'am.
is left, you just
Okay, ma'am. Okay, ma'am. Sure.
okay, okay. Dr. Sadhu, can you hear me?
Yes, ma'am. Yes.
Okay, so the first question we have from Mr. Akash Haldar. The first question is, how can one drone communicate with other drones? Are drones
Mhm.
using 4G network? And the second question he has asked that you have discussed here some communication challenges of UAV systems. Please, if you name some of those challenges, just the names, not the description, then we can note down the names of those challenges.
Challenges
Over
means
to you, sir.
whatever problem we faced.
No,
Here
actually, you have
challenges means
discussed some UAV systems. Like I think they want to also participate. He's also want to participate in that challenges, I think.
okay. So basically, what we faced here in India, we used we used some ad hoc type of network using Wi-Fi system or all these things and connected to the Wi-Fi to the all the drones and share the information to other drones. But whenever we go there, our system is not compatible to their communication system, but it was the 5G. So that problem not only faced by us, it was also faced by CMU and other top universities also. So this is a main problem you have to face. Well, you may face. I should not say have to, but for Indian people, it is very common when they go outside for this type of challenges. They may face this type of problem.
Okay, another question he has asked that is, how can one drone communicate with other drones? Are drones using a 4G network?
Yes, obviously there is a common Wi-Fi network, 4G. That network is accessed by everyone, and this is the way they share information, minimum exchange their information using ROS network, of course. Robotic operating system is here used to exchange information from one drone to another.
Mr. Omyo Sarkar has asked which software is used.
And as I told, a robotic operating system ROS platform is used for all the drone and all the vehicles, all robotic agents. Robotic operating system ROS, which is open source platform. This is used for here. And for coding, you can use Python, C++, anything. Even you can use MATLAB also. This is also actually whatever your coding language, you can code some codes. Suppose you want to code planner in MATLAB and a state estimator in Python and vision coding in C++. All can be interfaced using ROS, because you will publish some data and others will receive. So ROS will communicate with all the domains. So it will not be a problem. You can code in any language, but all can be interfaced through ROS.
Okay, another question here is asked that is, which radio frequency is being used for communication in drone?
That I cannot exactly remember what is the value of the frequency. Uh, Later I can share with you too.
Okay, okay, fine, sir. Any other questions? If you want to ask, questions have been left.
Anything asking?
No, I'm not
Okay.
asking to you. I'm
Okay.
asking to
Okay.
another. Okay. If anyone has any question, please raise
Yeah,
your hand.
actually, Honorable Vice Chancellor sir from IUST have some question. He's
Yes.
written something in chat box.
Let me unmute.
Okay. So
Yes,
Uh,
sir. Yes.
okay, it's
yes,
not a
sir.
question.
Please, sir.
I'm actually
Yes. I cannot listen.
Yeah, there is some audio
and
issue.
I enjoyed his lecture.
Thank you, sir.
In-depth knowledge about how drones work and especially their uses, which can be, again, as I said in my inaugural talk also, that this is going to be Thank you.
Thank you, sir.
Thank you, sir. There are two more questions. Dr. Sriparna, can I continue with?
Yeah. I should read out, or you are going to read now?
Yeah, okay, I'm just reading it out. Are you trying to find the shortest path? Or
Yeah,
is
of
it
course.
any feasible path from source to destination?
First of all, of
Anonymous
course,
attendee.
yes. Actually, feasibility is a like constant satisfaction. Of course, we are trying to find out the shortest path, but if the shortest path is not feasible, we cannot execute in real time. So, of course, there is a constant validation. So, once we are validating constants, automatically feasibility will be checked.
Hope the participant got the answer. Next is what algorithm you used to find and place bricks by drone? Question sent by Probal Roy.
Actually, that is done by Bangalore people. So, actually, challenge two, and challenge one done by Bangalore people. So, we did challenge one only in Kolkata. So, I cannot share the exact algorithm what they used, but generally, he used some brick picking technique using some magnetic gripper, where the bricks are magnetic material, and there is some magnet attached with the mm, brick end effector.
Okay, or maybe you can share your email ID so that
Yes, yes,
the participants can interact with you offline if anyone is
yes.
more interested or is continuing in this particular field of research, so
Yeah,
that
of
they can
course.
have some interaction with you. And also it would be kind enough, sir, if you can share us so that we can share with the attendees also the PPT of your lecture later
Uh,
time. If you can share some
uh,
material, some study material, some sort of material as a support of this talk. You can take
okay.
time because we are with the attendees next for next 5 days. So it will
Yes,
be
yes,
helpful.
okay.
We can share the through the WhatsApp group that we have. So I think no question is. I'm not finding any question in the question answer area. But like
Yeah, actually, few time earlier, that is in the starting of the session, there was one question asked. I forget his name. He was asking about how you are finding the obstacles, how the robots are knowing that this is an obstacle, it's not obstacle. So, if
Yeah,
Dr.
it
Sadhu
is.
can answer this question.
Yeah, generally we preferred using a lidar sensor here. So it's as I told, that point cloud, when a camera or some lidar sensor is on, it's returning some point cloud. So point cloud is that which is in the field, near field of view, something is there, then that particular XYZ points are returned as a point cloud. So if there is something, that means it is an obstacle. So that obstacle's corresponding points are returned as a point cloud, and from that point cloud we process it to know what is the obstacle shape, dimension, everything. So basically it is a use of sensor. There is nothing rocket science here. So it is all our open source codes are available for obstacle detection, everything. So what you need for that is a good quality camera and lidar sensors. So basically it's the sensor is required for that, or we can simulate these things in gazebo, as I
हाँ,
told you.
अभी क्या कुछ इन लोगों को लिए ये चाहिए, मतलब फीडबैक फॉर्म फिलअप करना है हर एक दिन के लिए, लास्ट दिन करेंगे?
maybe she is on mute. Sir, you please continue with.
Okay. So you can so people can use the ROS also. So for that testing of all the algorithm and obstacle detection. So without sensor, because sensors are very costly, so initially people can test in simulator like Gazebo, all these things. So these are the basic technique people generally using currently.
Okay, so that would be really kind of you if you whatever lecture material or study material you will be sharing with us there, if you please kindly give these resources that are freely available so that
Yeah, I can
uh,
show the ROS topic here. My screen is shared, na?
no.
Okay, just a minute. So my screen is now shared.
Yes, yes.
So this is the ROS wiki. You can uh, you can go through or start with robotics from this URL, the ROS wiki, where all the documentation and what is happening for robotics related softwares or all these things, everything you will find from the ROS wiki. These are all open source, and you can simulate your idea. You can code here everything, and there are there are lots of forums also. If you post your queries, you will face some problems. If you post your query, then people will answer you also.
Thank you for sharing this resource. Just as I was going through your interesting videos and the challenging task that you are doing, I
Yes.
have just one question. Like, as
Yes.
we are all doing in the simulation environment, so
Yes.
and these are all real life applications. Like the
Mhm.
delay, accuracy, all are very much crucial in
Yes.
any
Yes.
kind of real time applications, like sir. So how we
Yes.
can ensure like with the simulation results that we are getting and actual field testing that you are doing, what is the variation between the two in terms of
Yeah. Of
accuracy
course,
or latency?
there are. Yeah. Of course, there will be lots of issue when you after successful simulation. If you want to go for real time implementation, there will be lots of issue will come from communication issues. There will be some loose wire. There will be some takeoff problem. There will be battery issue in case of drone. So there are lots of problems. So we are facing these issues. Of course, we are facing, because in case of drone also it it cannot fly for more than 20 minutes. So for flying or testing for 20 minutes, we have to charge it for 2-3 hours. So these are lots of practical issues still not solved. But we in simulation we can test algorithms so that the algorithm should be ready. That's the point. These type of small little problems like communication, battery issues, take off flight time, all these things will be there, currently is there, because these are the state of that issue. We cannot solve these type of problems. But parallelly, if we face the algorithmic issue also, then we cannot identify where is the problem, whether it is some practical issues like communication or all these things, hardware issues, or my algorithm is faulty. That thing we cannot identify in this case. So what it is done, people generally do, they test their algorithm in such simulator, whether it is okay or not. Once they confirm that their algorithm is running properly, then we should go for real-time testing.
So basically what I got is sir that logic should be correct, and
Yes.
with the limited constraints the logic should be correctly run to achieve the desired results, and only
Yes,
that
yes,
is achieved then we can go for the practical deployment. And now
exactly.
practical application mostly of drones is in the surveillance,
Surveillance
is it
nowadays in, yeah, surveillance now in industry, object transportation, like Amazon
mhm.
delivery, and all these things are
Okay.
going on in
Okay,
warehouse
so
also.
warehouse also. Okay. So basically, so means you have already explained well that there are so many factors that may affect whenever we are going to real-time implementation.
Yes, yes,
But before
yes.
that, obviously, we should be correct enough in the simulation environment. So
Yeah.
one announcement for the participants that feedback link is shared in the chat box of today's lecture. So you please do that formalities that we'll be doing every day. And still, Dr. Sadhu is with us. So if you have any question.
Yes, I have one question actually. Okay, so
Yes.
if you can help us that what are the courses the participants can go through if someone have suppose no knowledge about robotics but they want to start learning or doing robotics. So what could be the subjects they should study to go for the to implement
So
robotics
yeah,
or
for
how
robot
to study or in what point of time? Yeah, sir.
yeah. So for robotics, if you want to someone want to work in robotics, then first of all, the person should be a good coder as well as good mathematician. Mathematician like linear programming, real analysis, differential algebra, all these things. So in depth, because everything work on mathematics, all the steps. So in a single sentence, that's why I told mathematics and coding, because only knowing mathematics will not be enough unless you are able to code and test it whether my mathematics is working or not. So these are the two things mainly. And after that, hardwares are always there, because hardware issues are always, because in India we cannot make till today we cannot develop that much, and we are not that much advanced in hardware. But in simulation we can, or testing algorithms we can do a lot mathematics and coding.
Okay. Okay, so you have
Yes,
already told the codes can be written in C, MATLAB, or any type of thing, and ROS will going to
yes,
take
yes,
care of that. So, what about the
yeah.
hardware? Means I am asking from someone who doesn't have, suppose, any knowledge about robotics. So, what could be the minimum hardware one can buy, or the minimum cost? What are the minimum requirements to start working in robotics? Is there any such?
So for minimum, there are people can, for simple robot development, they can start with Arduino or Raspberry Pi. Raspberry Pi will be better, because this is the cheaper one compared to or Jetson and all these things. And what regarding sensors are really very costly, because LiDAR is very costly. The Velodyne I have shown you, it's around mm, more than 10 lakh, I think. I cannot remember exactly. And another thing is that nowadays people are using the event based camera. Event based camera is something like as we human beings see the events, if there is any change in event, then we put our focus on that region. If there is change, that is in our focus. So camera is also nowadays came a state of the art cameras. So this type of camera generally focus on particular region or highlight that region if there is any change in that region. So that's why it's called event based camera. You can go to the ETH Zurich site for lots of updates on that. ETH Zurich.
Okay.
Yeah,
Meanwhile, okay. Yes, sir.
yeah.
You can continue.
No.
Okay, okay. Another question we got from Piyush Kanti
Mhm.
Datta Pramanik, that how important the role of FANETs in a small large scale UAV applications and what are the issues?
What is that? FN?
FANET,
FANET,
FANET.
FANET
Hmm.
in a small and large scale FANET in small and large scale UAV applications. What are the role of that FANET in that applications and what are the issues?
Uh, Actually, there are a lot of issue. Mainly, there are something like basically finance means communication and mobility, all these things, security issues. So basically, communication is the main thing in case of coordination, and security is also because someone can access. So basically, it is coming the point of coordination is happening without communication or with communication not. If it is happening with communication, then definitely there will be issue. But if it is happening without any communication among the agents, because such systems are also possible, agent can communicate without agent can better collaborate or coordinate without sharing any information among them. This is also possible. So if you look at the FANET, then this is also not a that much bigger factor if you are going for without any communication network. Because why I'm saying this, because when we human being move through a crowd, we don't talk to each other, and also we don't collide with each other. We just look at our surroundings and predict my neighbor's velocity and future position, and move accordingly. So we don't communicate with it with anyone, but we still move efficiently. So this type of system also possible. We are working on that also. Yeah.
Okay,
Next,
anyone has
please.
any question, please ask. Yes, there is no other question has been posted till now. So if anyone has any question, our eminent speaker is with us. You can answer your queries. Or you can raise your hand if you cannot type it in the Q&A section.
I think we can thank our eminent speaker
Thank you, madam.
on
Thank you for
behalf of the organizing committee for his illuminating and very highly technical talk with the demonstrative videos, which was really interesting. So yeah, the participants are with us for next 5 days. So if they have any question, they can reach to us. We will pass that to you. You can have some time to answer that, or they can reach to you if you can share your email ID in the chat box, and have some time and share some study material as requested to the participants. So thank you.
Thank you, madam. Thank you, everyone. Thank you, the participants.
So we are at the end of the today's session, Dr. Sriparna.
Yeah,
So,
just a small announcement. Feedback form link has been given to the chat box. Please fill it up, and all the active participants are only going to get the certificate. So registration is not enough. You have to actively participate in the FDP. So the link has been provided, and tomorrow we are going to have the session from 1 p.m. Yes, over to you, ma'am.
yeah, I think it's a very nice and illuminating talk for the beginning of our FDP with all technical details and demonstrations. I think participants have enjoyed a lot. Thank you very much, sir, for accepting our invitation and deliberating such a wonderful talk. Thank you very much.
Thank you.
And
Thank
thanks to the participants for their patient hearing, and after that so many questions came, so that reflects the fact that the talk was really interesting, and hope we will have such more interactive and interesting sessions in coming days. Thank you all, and thanks to our webinar team for their relentless effort for smooth conduction. Thank you all. Thank you, Sriparna madam.
Thank you, ma'am. Thank you to our eminent speaker, Dr. Arup Kumar Sadhu. Thank you, sir, and thank you to the webinar team. And thank you, and special mention thank you to all the participants over here. And thank you, everyone. So I think we can now close the session, ma'am.
Yeah, we can close the session, and we will meet again tomorrow at 1 p.m.
Yeah. So
Good night.
good night. Yeah. Good night,
Thank you.
everyone. Bye.